What I've done is just where we left off, where we have the binary, quite not straightforward to read, not easy to understand, but not too complicated either. So if I run the simulation, I press the switch, you notice it's still working as expected. Whenever I press and it comes on, so it means we are reading properly, and then we got rid of the digital read. So what I'm going to do is copy this across. This time I will leave the simulation, the compilation verification running on 774, but we got rid of the digital read. So if we go to the reference, let me pull this back as we on it. You notice we moved from 77 something to 680 bytes now. So we're on 680 bytes now. We are saving much more memory as we go on by getting rid of only one line. So let's see shift. So we've got bitwise shift. We go into bitwise shift. So if bitwise shift, what it does is basically just shift the binary to the left by the number that is specified by. So if you use too large memory space, basically you may need 5 Arduino boards to implement a simple application. One embedded applications, we don't have a lot of memory, and that is actually where computer architecture, that is where the master's level programming comes in. And also, if you have smaller memory, it means that the code can run more efficiently. We had a similar thing as having multiprocessing and then how we execute things. If you have large memory, remember dealing with floating point numbers takes longer time compared to integers, and similar as you are making use of bytes and bits and stuff. Okay, so if we say bitwise shifting, we are shifting it by the order of bits that we want to move across. So in this particular case, if we shift, let's say 1 by 0, we're still on the ones. If we shift it by 1 bit, then we go going on 2. Shifted by 2 bits, then we actually going to basically setting pin 4, or the same goes 3 is 8, or the way 8 is 256. So just order of bits. I can share the white screen and write it on there if we need to. So basically you've got 0, 0, 0, 0, all the way going. So if we do bitwise shifting of 0, we're basically not doing anything much, or we are not doing much in that. But if we shift it by 1, we are setting this one on. If we shift it, so 0 was to set that pin on, and then shift it by 1, we are setting this pin on. By 2, all the way going in that direction. So 0, and then, so if you by 3, brainer. So if you want this reference, reason why I'm jumping between these references is you can find it yourself, you can read more about it, you can get an understanding of it. We are interested in the pin 2 in this case. So the pin that we are interested in is already given a variable name. So we have the and, we understand it, we are testing it, and it is working. And we know that we said earlier we'll be making use of the button pin. So let's point it out. So we know we'll be making use of the button pin somehow. So how do we use it? Okay, we have the button pin. Now we have to shift the button pin by a certain number of bits, right? We have to shift it by a certain number of bits. So how do we shift the button pin by a certain number of bits? The button pin is as in create same thing as we have created here. So we have 0, 1, 2. So we remember when the bitwise shifting that we did earlier, we want to do the same thing, move it by 2. So we come here and we say 1, shift it by the number of places of the button pin. That goes to pin D, right? Okay. So similarly, as we did before, we expect this to work somehow, but we are dealing with bitwise shifting and binary and everything. So this actually says the right pin up. And then what we also want to say is that, okay, now we have sort of binary on there. We want to make sure that the very first bit is written into the switch, so we don't mistakenly write 0 or anything. So this part, the logic here, we achieve this. Basically, we just simply read the switch, or read the pin D, in B, so pin D2, and we want to, after reading it, we want to shift it all the way back down. So let's shift it all the way down to the button pin, so we don't mistakenly read a 0. So whatever logic we are created here, if it is a 1, we want it to come to the right bit, and then we write the 1 here. If it is a 0, we want to come to the right bit, and then we write it here. Good. So we expect that to work somehow. Run it. See if there are any errors. No errors. We are still on track. Okay. So that takes care of this style of writing. Please make sure you understand. Make sure you know how it's going, you know where we're going, and you know how to deal with it. Okay, so back to now we have, if the switch is low, we make use of digital write. So we know so far that we can use the port to do a write, as we have already done here by using digital write, sort of our own version of digital write, or register version of the digital write, to pull up the pin. Okay, so we are making use of port D, and on port D, what we want to do is write to the LED pin. Back to the whiteboard. So let's say we've got X again and Y. So we've got our X. Are we familiar with OR gate? The previous example meant both Michael and the students have to be present for the class to be on. But let's say if we are going for dinner, and the condition is either Michael or so Michael or the students can't be present before we start eating. So if the students are present, we will start eating. If Michael is present, we will start eating. If both of us are present, we will start eating. If none of us is there, nobody is going to eat. So the only scenario where an OR gate is 0 is both cases are 0. So let's use 4-bit now. And we have this 4-bit, and what we want to do is read the state of, write to the state of this pin. So if it is 1 and we do, we send a 1 to it, the output will be 1, right? If it is a 0 and we still want to write to it, and then we send a 1 to it, we expect the output to be 1. So in this case, we are using an OR. Yep, so this case is an OR gate that we use to set the pin. So to read the pin, we are doing AND gate. To set it, we are using OR gate. We talk about a case where we toggle the pin some other time. So back to our visual stuff, visual screen. Okay, stuff. Taking this time. Right, so to write to it is an AND, and to read from it is an OR. So let's find a way to read. To read from it is an and to write to it is an OR. So let's find a way to do bitwise. So the double. Please note double. Let me show you bitwise operators. Find it. So we've got the Boolean logic. The Boolean, you use the double for and then also double pipe symbol, or it's a pipe symbol for or. Let me see if it has bitwise on here. Because the bitwise is only one of them, so we are using bitwise. So bitwise, we are performing the and or on the individual bits. Because this one, something like if x is x or a, and then you are using something like integer and other stuff. But this one is when we are manipulating bits, we make use of this side. Okay, all those symbols on there. Perfect. I'm glad people are paying attention. Well done, happily. Okay, so we go to port E, and the bit we are interested in writing to is actually bit 5, but as the LED pin, so we can make use of that. So we take 1, and then we shift it to the position of the LED pin in terms of number of bits of the LED pin. Then we want to do an OR, so we say OR and port D. It's like X equals X plus 1, isn't it? So we do OR of port D, and then we write a 1 to it. Now, to this makes sense, let's try it again and then make sure there are no errors. When we run it, we notice it works perfectly, so this replaces digital write, and it seems to work all right. Now, if not, we want to toggle it, or we want to find the inverse of it or switch it off. So basically, if we have this being set in the pin, we go back. We've got the bitwise not, basically just find the inverse of it. If it is not, then simply find the inverse of it. So hopefully that makes sense to all of us. I am running this image and didn't respond. Go back in there, and we can put a not on there. You can find it on there. Yep. So basically what we are saying is that just find the opposite of that, or set it up, because this sets the pin, and if you want to deassert it or send a 0, you find the inverse of that. Good. Run the simulation and respond. Stop it right there. See what I'm doing wrong, if I'm doing anything wrong. Or on there and or on there. Back to the whiteboard. Fix any issue that we have. So let's say we have our X. So far we've made use of the and then we've made use of the or. So if our X is equal to 0, 1, 0, and then we have our Y, and what we want to do is to toggle this. Let's say if we do an AND with this. So if we do an AND, and if it is 0, it will be 0. If the pin is 0, it will be 0. And then if we toggle it, so first of all, we do an AND, then we toggle it. So if we toggle it, we expect the output to be a 1. So if it is on, it just simply stay on in that sense, because we do an and then we end up with that. Now it is, if the value on there is 0 instead of a 1, and then we do an and with, clear the screen, clear the screen, clear the unnecessary parts so we don't confuse the explanation. Actually enough. Perfect. Alternative example that makes it better. So we go 0, 0, we set all these to 0, and then we set that pin that we are interested in to a 1. So if we do an AND by setting it to a 1, the result is a 1. If we toggle it afterwards, so we have the AND and then we do a toggle, and it becomes a 0. So we managed to do, first of all, do an AND, and then it becomes a 0, which is a NAND gate. That is the logic. Now, if let's say we put the data there is a 0, not 1, and then we do an AND, we expect the second case. Let's get rid of this. If it will work, not what I'm looking for, I'm looking for that. So in this case, if it's 0 and we set that bit to 1 and do an AND, we get 0. And then if we do not that way, or an AND gate in its case, we end up with a 1. So you notice that what we have managed to implement is something that converts a bit to its opposite form. So if it is a 1, it ends up as a 0. If it is a 0, it ends as a 1. And we have basically just combined the AND gate, I use this for AND, and then not of that. So we say the not AND. So first we perform the AND gate, and then afterwards we perform the not gate, which is an AND. So back to sharing screen. Everybody accepts that, everybody understands that, and hopefully it is all good news to everybody's ears. Back to the screen. So back to the screen now. And the issue or the mistake that I made there, if you simulate it, you notice when I press, it will stay on because I wasn't toggling it, just stay on. So how to fix it? Change this to an AND. So first of all, we set it to the bit that we want, and then we perform an AND, and then we toggle it. So run the simulation. And it works the same way that it's worked before. The same brilliant code that we had right from the beginning has been reduced to this. And if we run it on, so copy, stop the simulation. If we run it on here, we started off 892, if I remember correctly, or around 89 something, and reduced to 680 by introducing register manipulation or understanding of the registry. Let's see how far we've wanted to reduce the code to here. We've managed to reduce the code to 462. Now, if you remember, when we started, just the setup and the loop alone to 444, which means our code now has reduced by half, and the actual implementation that we have added occupies only 62 bytes.